Last time, we decided to use gradient descent to train our neural network so it could make better predictions of your score on a test based on how many hours you slept and how many hours you studied the night before. To perform gradient descent, we need an equation and some code for our gradient dj dw. Our weights w are spread across two matrices, w1 and w2. We'll separate our dj dw computation in the same way, by computing dj dw1 and dj dw2 independently. We should have just as many gradient values as weight values, so when we're done, our matrices dj dw1 and dj dw2 will be the same size as w1 and w2. Let's work on dj dw2 first. The sum in our cost function adds the error from each example to create an overall cost. We'll take advantage of the sum rule in differentiation, which says that the derivative of the sums equals the sum of the derivatives. We can move our sigma outside and just worry about the derivative of the inside expression first. To keep things simple, we'll temporarily forget about our summation. Once we've computed dj dw for a single example, we'll go back and add all our individual derivative terms together. We can now evaluate our first derivative. The power rule tells us to bring down our exponent 2 and multiply. To finish our derivative, we need to apply the chain rule. The chain rule tells us how to take the derivative of a function inside of a function, and generally says that we take the derivative of the outside function and multiply it by the derivative of the inside function. One way to express the chain rule is as the product of derivatives. This will come in very handy as we progress through backpropagation. In fact, a better name for backpropagation might be, don't stop doing the chain rule ever. We've taken the derivative of the outside of our cost function. Now we need to multiply it by the derivative of the inside. Y is just our test scores, which won't change, so the derivative of y, a constant with respect to w, is 0. Y hat, on the other hand, does change with respect to w2, so we'll apply the chain rule and multiply our results by minus dy hat dw2. We now need to think about the derivative of y hat with respect to w2. Equation 4 tells us that y hat is our activation function of z3, so it will be helpful to apply the chain rule again to break dy hat dw2 into dy hat dz3 times dz3 dw2. To find the rate of change of y hat with respect to z3, we need to differentiate our sigmoid activation function with respect to z. Now is a good time to add a new Python method for our derivative of our sigmoid function, sigmoid prime. Our derivative should be largest where our sigmoid function is the steepest, at the value z equals 0. We can now replace dy hat dz3 with f prime of z3. Our final piece of the puzzle is dz3 dw2. This term represents the change of z, our third layer activity, with respect to the weights in the second layer. z3 is the matrix product of our activities, a2, and our weights, w2. The activities from layer 2 are multiplied by their corresponding weights and added together to yield z3. If we focus on a single synapse for a moment, we see a simple linear relationship between w and z, where a is the slope. So for each synapse, dz dw2 is just the activation a on that synapse. Another way to think about what the calculus is doing here is that it is backpropagating the error to each weight. By multiplying by the activity on each synapse, the weights that contribute more to the overall error will have larger activations, yield larger dj dw2 values, and will be changed more when we perform gradient descent. We need to be careful with our dimensionality here, and if we're clever, we can take care of that summation we got rid of earlier. The first part of our equation, y minus y hat, is of the same dimension as our output data, 3 by 1. F prime of z3 is of the same size, and our first operation is a scalar multiplication. Our resulting 3 by 1 matrix is referred to as the backpropagating error delta 3. We determined that dz3 dw2 is equal to the activity of each synapse. Each value in delta 3 needs to be multiplied by each activity. We can achieve this by transposing A2 and matrix multiplying by delta 3. What's cool here is that the matrix multiplication also takes care of our earlier omission. it adds up the dJDW terms across all our examples. Another way to think about what's happening here is that each example our algorithm sees has a certain cost and a certain gradient. The gradient with respect to each example pulls our gradient descent algorithm in a certain direction. It's like every example gets a vote on which way is downhill, and when we perform batch gradient descent, we just add together everyone's vote, call it downhill, and move in that direction. We'll code up our gradients in Python in a new method, cost function prime. NumPy's multiply method performs element-wise multiplication, and the dot method performs matrix multiplication. We now have one final term to compute, dJDW1. The derivation begins the same way as before, by computing the derivative through our final layer. First dj dy hat, then dy hat dz3. We now take the derivative across our synapses, which is a little different from our job last time, which was computing the derivative with respect to the weights on our synapses. There's still a nice linear relationship along each synapse, but now we're interested in the rate of change of z3 with respect to a2. Now the slope is just equal to the weight value for that synapse. We can achieve this mathematically by multiplying by W2 transpose. Our next term to work on is dA2 dz2. This step is just like the derivative across our layer 3 neurons, so we can just multiply by f prime of z2. Our final computation here is dz2 dw1. This is very similar to our dz3 dw2 computation. There is a simple linear relationship on the synapses between z and w1. In this case, though, the slope is the input value x. We can use the same technique as last time and multiply by x transpose, effectively applying the derivative and adding our dJDW1s together across all our examples. All that's left is to code this equation in Python. What's cool here is that if we want to make a deeper neural network, we could just stack a bunch of these operations together. So how should we change our w's to decrease our cost? We can now compute dJDW, which tells us which way is uphill in our 9-dimensional optimization space. If we move this way by adding a scalar times our derivative to all of our weights, our cost will increase. And if we do the opposite, subtract our gradient from our weights, we will move downhill and reduce our cost. This simple step downhill is the core of gradient descent, and a key part of how even very sophisticated learning algorithms are trained. Next time, we'll perform numerical gradient checking to make sure our math is correct.